Hello, I'm Dave Tabb, a bioinformatics trainer over at Institut Pasteur. Today I would like to do a quick demonstration of how to use the TopPIC search engine for top-down identification. Now I will be using three files that we've collected in the past at this lab for E. coli proteomes as our demonstrator. And you can see that they are found over in PXD 019247. That's over on Proteome Exchange. Now that file contains a whole bunch of different raw files. I'm just using these three from November 8th of 2016. Certainly you can use data from other organisms as well, but this one is from E. coli because it's a nice compact genome for us to work with. I've already downloaded a FASTA sequence database for the reference proteome for E. coli K12, and I've also created a variable modifications file. I'm going to show that in a minute. It's over here. But the important thing to note at the moment is that it contains the possibility of oxidation on methionine and disulfide loss of two losses of hydrogen on a pair of cysteines. So we'll come back to that in a moment. But for now, let's start with the fact that these raw files that I've downloaded had to be converted to MZML first for me to be able to do this search. TopPIC doesn't read, the TopFD algorithm doesn't read raw files natively, so we had to convert these to MZML first, and I did that in ProteoWizard MS Convert. I didn't do anything terribly special there, except that I use peak picking for MS and MS scans, and I told it to zip the contents. Okay, so we have these three MZML files, and we need to prep them for database search. Now, ordinarily in bottom-up identification, we can just go ahead and run our search algorithm against the MZML files. But in this case, we're going to have to do deconvolution first. And the reason for this is that a given fragment ion in a tandem mass spectrum for a proteoform frequently appears at multiple charge states, and it frequently appears in many isotopes. So the process of deconvolution is going to combine multiple charges of each fragment and multiple isotopes of each fragment into a single peak that it will store as an MS Align file. Now the software that we use for that is TopFD. TopFD is part of the TopPIC Suite toolkit, so when you download TopPIC Suite you get this along with it. Here I'm using the GUI version of TopFD. I would just note that my preference is typically to use the command line software because then I can run everything through a batch file. But I realize that a lot of people find it easier to use graphical user interface software. So I need to first tell it where to find my raw files. Now I've created a directory off of D on this computer with the name PXD blah blah blah. That's where I'm storing these files, and you can see that the MZMLs all show up right there. I'm going to select all three and click Open. And you can see that they're added to a queue at the top of the screen. Now, the software is going to be set to defaults, and I definitely want to check those, because if I'm looking for a really, really large proteoform, it might be that the ceiling on charge or mass, your ceiling, the charge ceiling and the mass ceiling, that those might be set too low. In this case, I feel very confident that essentially all of my proteoforms are charged less than plus 30, and are below 70,000 Daltons in mass. The signal to noise ratios I will leave unchanged. The precursor window size and mass to charge error are already set to something appropriate for thermo FT instruments. However, I note that the thread number is set to 1. Now if you simply leave everything as default, you're going to only use one processor core on this computer, and this one has 20, so why would I do that? I'll give it, let's say, 10 processor cores. This fragmentation file part may not seem very sensible at first, but I would explain that TopPIC is able to detect whether ETD or HCD, or CID for that matter, were used to produce each tandem mass spectrum. In the case of file, the software is informed that I want it to look in the raw files, in the MZML files, and determine which fragmentation type is appropriate for each scan. Now, ordinarily, if I were going to visualize each of the proteoform spectrum matches that TopPIC produced, I would want to generate HTML files. But if you're just looking for a final table of identifications and not trying to map them back to spectra, you can avoid this step and it'll produce far less mess on your hard drive, a huge spray of tiny text files. In this case, I don't want to do that, so I'm going to unclick that. But the results will be much less descriptive as a result. Okay, with that said, I can simply click Start, and the software will begin processing my 3 MZML files. In the old days, when we had mostly single-core computers, this kind of process could take all day. But the fact that I have 10 processor cores to distribute that work across makes this run much faster. Now, I'm going to see if I can make my screen a little taller. Oop, I can't. There. Here we go. No, it's not going to do that. So I'm going to have to hold this guy down and drag him around. Not going to work so well. That's fine. The important thing is that TopFD, when it runs, gives a description of how it was run. And you might think, oh, I got to copy all this stuff down right quick. But the reality is that this is going to be written in the MS Align files that the software writes. So it's not just making the deconvolutions, it's also reporting how those deconvolutions were run. I note that the version I'm using is TopFD 1.5.3. This the 1.5 release is just a couple months old at this point, and they've gone through a few revisions to it, but it seems to be a really solid code base. I've primarily worked with version 1.4.13 that I used for a manuscript we're doing. So 1.5.3 is the most recent I had available at the time of this recording. So we can ask, how are things going? And we see that each of these raw files contains a fair number of spectra, something like 10,000 apiece, and that is simply going to take a lot of time to work our way through. We can ask what kind of load this is imposing on our computer by using Task Manager. I think I mentioned that I had 20 processor cores for this machine. We can see, though, that because I allowed it to use only 10, our CPU usage is not all the way up to the top. And all those cores are all being used pretty aggressively. We can also see that there's a fair bit of memory load from this software. At the moment, it's not even using 10 gigabytes of the RAM that this computer has. So it's reasonably memory efficient. You don't have to have an extremely high-end workstation to do this with. At home, I'm using a 6-core Xeon processor from 10 years ago, and that's still quite fast enough for doing these searches. So at the first stage, we're going to process each of these scans, and each of these tandem mass spectra is going to be reduced to fragment ions in either neutral or +1 form. Different top-down algorithms choose to report neutral masses or ionic +1 masses to their outputs. So we see that the first file has now finished this deconvolution process, and the next stage that it's going to go through is feature detection. So naturally, the tandem mass spectrum doesn't contain the only information pertinent to identifying each tandem mass spectrum. We also need to know what was the precursor charge state, and from that, what was the precursor mass. That means we need to be able to detect to as great a mass accuracy as possible what the mass to charge value of the precursor is. We have multiple isotopes of it, and we may even have multiple charges of the precursor in the mass spectrum. So TopFD is going to write each spectrum as a separate MS deconvolution. It's going to have, however, multiple tandem mass spectra in some cases for the same precursor. You might have the precursor appearing at +7 and +8. The software might be able to combine information of the +7 and +8 precursors to get a more accurate mass for a single feature that relates to them both. So even though the tandem mass spectra were produced from different charges in the MS scan, it might be that the same feature relates to both of them. Okay, so we're already onto the second file. We see that the time required is not punitive, but there's not a huge amount of stuff for me to say. So I will try to think of what else I would report on this. Naturally, if you have spectra that you've produced from an older and slower instrument, you're quite likely to see a smaller number of spectra captured. If you have a sample that is not a whole cell lysate like these are, but rather proteins cut from a band of a gel, or if you have done some sort of enrichment for proteins, you may find that the number of spectra you collect is far less than this. These data were collected on an Orbitrap Fusion Lumos, which is not the oldest kind of instrument you might have used for top-down proteomics, but as you can note from the file names, they were collected back in 2017. And 5 years ago, the instruments were not quite as hot as they are today for collecting lots and lots of high-quality tandem mass spectra. Although this example makes use of thermo raw files, I would note that you are not limited to doing proteomics, top-down proteomics on thermo Orbitrap class instruments. Some of the data that we've worked with have also come from Bruker Maxis instruments. And the Bruker Maxis is actually quite a capable top-down platform. We were able to identify a fair number of high-charge precursors from that. So I'm as an outsider to the top-down community, I would have to say that my experience of the software within this community has been very encouraging. It has gained quite a lot of maturity since the last time I really looked at top-down. Okay, so we are working our way to the end of the second file. We're almost to the place where we can launch our search. If you don't mind, I'm going to bring the TopPIC user interface up alongside it because we have a fair number of things we need to configure. TopFD will keep running in the background and will only start this job when it is finished. So TopPIC, the TopPIC user interface has a similar kind of setup. We still need to add the spectrum files to our queue. We're going to need to specify a sequence database, and there are a bunch of other basic and advanced parameters we will also want to fill out. So let's just start populating that. For the database file, I think I mentioned that I've already created I created a sequence database just by downloading it from Uniprot. UP blah 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 625 is the number for the reference proteome for this species. Oh, I want to mention that in the process of feature detection, you're sometimes going to see these warnings. Those warnings just refer to cases in which getting a nice integrated chromatogram for a feature was not feasible. So don't worry too much about the warnings. If they were showstoppers, they would be called errors rather than warnings. Okay, so we're going to specify this sequence database that's now registered up here. I'm going to wait to do the spectrum files last because they're still deconvolving over here. And in basic parameters, I need to define how this experiment was produced. Now it might be that I've used, that I've reduced disulfide bonds and then treated them with iodoacetamide to carbamethylate them. I did not, however, do that. In this case, the disulfides are left intact, so I want to leave the fixed modifications set to none. Some people might prefer to control their false discovery rates by the target decoy approach. In this case, I'm going to just filter on the basis of e-values, so I don't need to include decoys in my database, thus my search can run faster. Because we are using TopFD for our deconvolutions, we don't need to flag that there is no feature file. It is going to be produced. We don't need to worry about keeping decoy identifications because we're not using a decoy database. Again, I'm going to try to go for a very compact output, so I'm not going to generate HTML files. I don't need to keep the intermediate files either. Now this e-value thing might seem a little unfamiliar if you're not familiar with software like the MSGF plus search engine. The spectrum e-value is the scoring approach that TopPIC uses for making a score that can be used to determine which spectra have been identified successfully and which ones have been identified poorly. And as a result, we can use e-value at a value of 0.01 to say this is a score for this spectrum that would only have produced a match this good in random sequences 1% or less of the time. And we can perform that filtering not just on the proteoform spectrum match level, but also on the proteoform level. We may certainly collect many spectra for a given proteoform, so we can filter those on this e-value property as well. Again, we're going to just stick with the defaults because the defaults work really well for Orbitrap class data, so I'm going to use mass error tolerance of 15 ppm. Now this other feature might seem a little weird, the prism cluster error tolerance. So a prism is a proteoform spectrum match. We use prism rather than PSM from bottom-up proteomics. And we see that we have this really wide tolerance. The reason we do this is that it's quite easy in the case of looking at these precursors to make a plus or minus 1 Dalton error on the mass scale, because we have the possibility of picking the wrong monoisotope for each peak, for each precursor. So we're going to keep that fairly wide, and it allows the software to find more copies of each proteoform that have been identified independently. Okay, for advanced parameters, first off, we're going to need to look for mass shifts because we're allowing for some number of post-translational modifications on these proteoforms. If I set this to 0, the software will find no PTMs whatsoever. If I set it to 1, it's going to allow for one region of mismatch between the spectrum, the ladder of peaks seen in the spectrum, and what the ladder should look like from the proteoform. If I want to look more extensively for PTMs, I would look for the option 2. But 1 is pretty good if you're just trying to spot the occasional oxidation and the occasional cysteine disulfide. I wanted to note back here, TopFD has finished, so we're all clear on that stage. We can go ahead to add the peaks here. All right, so we're going to consider each each N-terminus in 4 different forms. It might be that the N-terminus is intact all the way out to residue 1, and it doesn't have an acetylation on it. It might be that it has the N-terminal methionine chopped off, in which case the proteoform starts with residue 2. It might be either of those cases with an acetylation added to it. Okay, so once again, I have a lot of CPU cores. This time I'm going to just use all 20 of them because why should we wait, right? I'm not going to mess with these other parameters, but I do need to specify a modification file. I mentioned at the start we were going to look for oxidations and disulfides. These numbers, by the way, I'll try to walk through this command. This is a modification we will call oxidation. That's the name that we pulled from Unimod. We have a mass shift of 15.9949 from each of these masses. It can only occur on methionine. Naturally, that's a little limiting. There are some amino acids that can oxidize above and beyond methionine. It can occur on methionine at any position, and in Unimod, it has the number 35. Here I've used kind of an unusual coding for disulfides in that I'm looking for a single modification called disulfide that accounts for the mass shift on a pair of cysteines, and yet I'm allowing it to put this on a single cysteine. I'm doing this because I don't want each disulfide to count as 2 mass shifts. I want each disulfide to count as 1. And the reason for this is that I've only allowed for 1 mass mismatch error in TopPIC. Do you remember that we set the maximum number of mass shifts to 1? So if I code this as 2 half disulfides, it won't find them. But if I look for a single disulfide with a -2 shift, it will find it. Okay, but I do need to tell it where to find this modification file. I have included it in the same directory along with everything else, just called variable mods.txt. Okay, the MI score threshold talks about the localization of these PTMs. But there's still one thing I need to do. Back on the files page, I now need to add my spectrum files. Now, you might have expected that it was going to have me look for RAWs or MZMLs, but instead, TopPIC is going to request that I look for the output files, the MS Align files, that were created by TopFD. So I simply select these 3, click Open, and those are added to my queue. I also want to make the point here that I am making a single TopPIC run for all 3 of these raw files. It's going to give me a report about each of the 3 raw files, but I also want to create a conjoint report. I always call it conjoint. It's just the name I use to remind me what I'm looking for. it's going to create a single conjoint report that lists all prisms from all 3 files, and also another report that's going to give me all proteoforms seen in any of the 3 raw files. So that's really valuable to me. I want to have that file created. Okay, and with that, it's time for me to click Start. Again, the software is going to spit out its assessment of all the variables I gave it up top. I can roll back and look at some of those values. But at base, what I'm going to see is the same sort of percentage crawl as it works its way through this collection of files. This is not going to be an immediate result, but it is relatively quick. I guess I always ask myself, what is an appropriate amount of time for software to run on one of these raw files? And I say to myself, all right, I had 3 experiments that each cost me 90 minutes to generate on the mass spec, so I could allow at least that much time for the search to progress. In this case, we see that the search is going to take a few minutes. So the non-PSM filtering is the non-PTM filtering is a case where we want to look for each of these proteoforms derived from the sequence database with no PTMs on board. Now, we don't have a really huge number of PTMs under consideration, but it is going to have to perform a single PTM filtering stage in order to find any occurrences of oxidation and disulfides. I think it might be worth noting, while we're waiting for this, that we have a huge number of files that are being created as TopPIC runs. These are the temporary files that it mentioned. Happily, a lot of those are going to vanish when the search finishes. But I think it might be useful if we were to spend a moment looking at the MS2 MS Align file. So I'm going to just drag that over to my text editor for a moment. Remember, I said that TopFD, as it runs, is going to report its settings at the top of each file, and then it's going to give me a description of individual tandem mass spectra. Now, if I page down a little bit, the ones that occur at the very start of the run tend to be kind of uninformative spectra. But if I pull down to maybe the middle of the file, you can see that each of the tandem mass spectra is represented by a begin ions block with a whole bunch of characteristics of the spectrum, all the way down to an end ions block. So we can see that the scan number is 5179, drawn from this raw file. That part is not too unclear, I think. The retention time is 3,938 seconds. This is an MS2, not an MS3. Its activation was ETD. I can see that the MS1 scan that was used to select this target for fragmentation was 5173. The MS itself was 5179, so that makes sense. And we're storing information like the precursor mass to charge value, the charge at which it was located, and from that the mass that was extrapolated. We also have this nice intensity feature. So if you're trying to ask, do I have a better chance of identifying tandem mass spectra that are intense signals versus those that are not intense signals, I'm going to guess that I don't think I'm going too far out on a limb to say, yes, you have a better chance of identifying intense signals. You can do that from the information that's reported in these MS2 MS Align files. If I keep dropping down, I see something that looks, for all the world, like an MGF file. I think many people are familiar with mascot generic files as a common text format for these. Here we see that we have mass values, intensity values, and charge values. So originally, the peaks of the spectrum might have been represented in M/Z order, but when we see them here, we're being given masses back rather than M/Z values. All right. So we've got our variable modifications, we've got our MS2 Align files generated by TopFD, and now TopPIC is going ahead to run. We see that the non-PTM filtering step on the first file is nearly finished, and in just a moment we should see it progress on to the next stage, which is the 1 ppm filtering. Now, I would note that even though this computer has a tremendous amount of CPU power, it's barely touching that. I gave it access to use all 20 cores, but it's barely using a quarter of the CPU's, the pair of CPU's power to do this search. One of the things that people don't understand is that we frequently find the limitations to search speed are not just CPU. Instead, the software is doing a lot of filtering back and forth with the sequence database. And that sequence database has a very large number of possibilities. As a result, what we have is a limitation in moving things from the hard drive into memory for this. It's not simply caching all of it in RAM, but rather doing a lot of this filtering through indexing on the sequence database on disk. As a result, if you were able to do this search from an SSD, a solid state drive, rather than a spinning hard drive, you would likely see a much better throughput for the search. So having large numbers of CPU cores is great, but it's often better to have good I/O throughput, better disk throughput. I think there's one other thing that's really worth describing before we speed up the video and zip through to the next stage. And that is when we do a search in top-down proteomics, we frequently want to do something called a truncation search. Now, I'm not just talking about the N-terminal methionine. Certainly, we want to have consider the protein sequence with and without that N-terminal methionine. That's something that TopPIC is going to do. But we should also consider the possibility that we have more egregious truncations of a sequence. What if, for example, one of these protein sequences has a signal peptide? That signal peptide would be removed from the N-terminus, and so you might be missing 20-some amino acids from the N-terminus. If we're going to search for those possibilities, we need to be able to do a truncation search that considers the possibility that we chop amino acids off the N-terminus, or chop amino acids off the C-terminus, or consider the proteoforms that would result if we chopped amino acids off of both the N-terminus and the C-terminus. In a case like that, we have 4 different searches to perform. We have the intact sequence plus or minus initial methionine. We have the prefix search where we're chopping things only off the C-terminus, the suffix search where we're chopping things only off the N-terminus, and the double cut search where we're cutting things off of both. All 4 of those searches happen in TopPIC automatically. Now the software is going to decide which of the results from those 4 possibilities it's going to report for each spectrum, and it computes the expectation values separately for each of those searches, because there are far more possible sequences where you can chop from either end of the sequence than there are if you disallow that kind of chopping. So all 4 of those searches are taking place simultaneously. Now we see that the software has finished its non-PTM search for the first of the raw files, and now it's proceeding to the 1 PTM search. You can see why I wanted to restrict the software from looking for 2 regions of mismatch. For a demonstration video, that's way too long. Now, this search could also take an hour or so, and I don't think you want to be sitting here watching all that. So at this point, I'm going to stop my monologue so that I can speed up the video in that part of the process. So I'll see you in just a minute, and may our search continue successfully. As you can see, the searches for each of the 3 files have passed through the no PTM stage, the 1 PTM stage, and then e-value computation. At this point, though, we've moved past the outputs for the individual raw files and are working our way towards a cumulative summary of everything. One of the things that we see is that the MS Align files that we used as inputs are going to be combined together in one big MS Align file that represents everything that was included in the analysis. So the merging files, the merging MS Align files, and the merging feature files is just how we kick off that process. One of the things that this allows us to do, this feature of creating a single conjoint report, is to assemble a master list of all proteoforms detected in any of the 3 experiments. So it might be that we detected 500 proteoforms in one, 500 proteoforms in the second, and 500 in the third, and yet cumulatively, that's not likely to be 1,500 distinct proteoforms. There's, generally speaking, especially in this case where we have 3 technical replicates, a huge degree of overlap in the proteoforms represented by each experiment. So the software will do this clustering in a way that allows us to detect proteoforms in common among the 3 experiments. I think in my experience with the software so far, I've merged up to 18 raw files in a single conjoint assembly. So that's rather useful when you're trying to put together a cumulative report. Consider particularly the case when you have different fractions. As I said, these are just technical replicates, so they wouldn't really benefit from this. But if you have multiple fractions from a gel separation or whatever upstream, it's likely that the proteoforms and even the accessions you see in each raw file will differ from each other rather substantially. In this case, we expect that the proteoform roster for one of these files is a pretty good representation of what we might find in one of the others. This PTM characterization process is one that's worth saying something about, because the way that TopPIC does it is rather special. TopPIC is expecting, in the way we've configured it, one place of mismatch between what the spectrum peak ladder says and what we predict from a given proteoform sequence. The software does not, at the initial search stage, try to interpret that. It just tries to say, well, there's a gap here, a mass gap of such and such between these peaks, and I have alignment on either side of it, but not at that gap. So the PTM characterization process that we saw once for each of the raw files and now once for the whole conjoint set is trying to interpret that mass shift in light of the PTMs that you supplied. I think you'll recall that in this case we've supplied methionine sulfoxide, the oxidation of methionine, and also the disulfide bridges as a PTM. So the software in version 1.5.3 allows each mass gap to be interpreted as any of the mass shifts that you've made available to it. And one of the very nice features of TopPIC is that it will go about trying to localize the PTMs in order to tell you which of the possible amino acids on which this modification could be placed is the best guess for you. Okay, so the PTM characterization process is really important for that. Certainly, if you want to evaluate PTM placement more aggressively, you would not just look for one mass gap, but two per prism. But that would make the search run longer, and I didn't want to do that for this particular search. Certainly, if you have a very large number of modifications on individual proteoforms, more than two, which is not that uncommon an outcome in modified proteins, you should probably look at using TopMG, which is another tool that also ships with the TopPIC suite. TopMG is a whole lot better for allowing for up to 5 modifications on an individual proteoform. And with that, we're finished. TopPIC has completed. In this case, we had 3 raw files, each of which took about 40 minutes to process. If we click over to the folder that we started with, we see that we have quite a few more files in there than we started with. We started with a FASTA file. Now we have an index to making sense of that FASTA file. We have these feature files that represent the individual features seen in the MS scans that relate to tandem MS. We have the MS Align files that were created to store the deconvolved peak lists, the MZML files that we started with. We also have a fair number of TSV files. TSV stands for Tab Separated Values. Each of these can be opened in Microsoft Excel or any other spreadsheet, or R for that matter, in order to interpret what these files represent. You can see that we have a set of 4 files produced for each of the raw files. This is because we're going to get the PRISM files, which represent the proteoform spectrum matches, each on its own row. One that represents the set of prisms that would have passed single file filtering, which is to say not looking at them as a conjoint set, but looking at each raw file individually. And we have the proteoform and proteoform single files. What you can see is that the PRISM file with a size just over a megabyte is roughly 3 times the size of the proteoform file, which is to say to us that each proteoform may occur in multiple spectra, and each spectrum matched to that proteoform is a row in this file, whereas each proteoform individually is a row in this file. I think you recall that I asked for a conjoint report. Those conjoint reports also have their very own reports, both in this single filtering and conjoint filtering stage. So we had 3 raw files, each producing about a megabyte of TSV in the PRISM files. Together, it's not surprising that they were about 3.5 megabytes. Right. So that's the outcome. We also have our results in XML format if you want to dig through them that way. It's often a lot easier to do that if you have, if you're trying to make a really intelligent parsing of features from within these files. But I'll probably record a separate video in which we actually read the files and interpret what has come from them. For now, though, I hope that you feel that you are more familiar with TopFD for deconvolution and TopPIC for identification of proteoforms, and I hope that you'll keep checking this channel for more videos as we go. Thank you very much.